Yesterday we defined moments using force. So the moment is defined by two things. This is moment R, and this is force. So when we are talking about those two properties, you need to be careful because let's say we have a cantilever beam, and this is my moment center. When I apply a force to it, we need to decouple this force into two forces. One is perpendicular to the momentum. The other one is going to be parallel to the momentum. When it's parallel to momentum, it's not going to create any moment. Only when this force is perpendicular to the momentum, it will fall into this formula, and we need to calculate for the moment. So in this case, we would need to know the angle between the force and the momentum, depending on whether you choose your angle. If the angle is using this position, then it's going to be sine. If you are using the angle over here, then it should be cosine. So I cannot tell you which one you should use, whether you're going to use cosine or sine, it depending on which angle you're talking about. Okay? So when you are doing this thing, in this case, the force is actually F sine theta. And the other thing we need to determine is direction. If it's clockwise, then it's negative. If it's counterclockwise, then it's positive. Okay? Two-dimensional is not so difficult to handle. You only need to know how long, what is the distance of the momentum, and which force you're going to use as your applied force. Use the projected value perpendicular to the momentum, and you should be able to use this formula pretty straightforward. However, if it's three-dimensional, it's going to be a little bit tedious for you to calculate the effective moment. So most likely, when you have three-dimensional problem, you need to identify x, y, z axis of your system. And when you are dealing with this, there are two vectors you need to deal with. One is moment arm, the other one is force. When you have those two properties, it also implies one thing. That is, the moment is also a vector. So when this is a vector, you would need to use a formula like this. So you would need to know, let's say this is my reference, moment center. Oh. And my cantilever beam is sticking up at this position. Then I have dx, dy, dz. Meanwhile, I'm applying a force to this cantilever beam at this position with in this case, the moment becomes cross product of those two vectors. When we are talking about cross product, the first row is going to be I, j, and k. The second row is going to be dx, dy. The third row is going to be fx, fy, fz. Does the order of those two rows matter? Yes, it is. If you put f in the second row and d in the third row, you're going to find the calculated result is going to have a negative sign in front of it. Okay? So be sure you put that in the correct order. Okay? So when you are doing this one, yesterday we talked about this a little bit. You need to follow the sequence. So it's going to be dy fz I plus dz fx j plus dx fy. When you are dealing with the calculation order, I would suggest you put k together, I together, and j together, because it will be easier for you to calculate. Okay? A lot of times you guys just put it in a line, and you just forget which one should be added together or subtract from each other. So the number is a little bit weird to me. In this case, it's going to be y fx a dx z dx dz fy I j. And if it's this direction, it's positive. If it's this direction, then you are negative. So you just add those numbers together, you get your k value. You put these two numbers together, you get a j value, and you put these two numbers together, you get your I value. Is that straightforward? Everybody understand what I'm talking about? This is going to be a little bit tedious, so be sure you practice this a lot of times. Yes?
Can we just do the, instead of like having to worry about shifting the lines around, can we just do the I and J on the outside and then?
I don't care how you process that, as long as you know how to do this. This is because the reason I didn't explain that method is because I realized not everybody is learning the same thing. So this one is offered in the textbook. Okay, so I just go through this one. Personally, I don't like this, but this is taught in class. So some of you guys might wonder, when you are doing this, you have I cross product j equals to k, j cross product k equals to I, k cross product j equals to k cross product I equals to j. And there are many formulas you need to remember, right? So how do you remember those kind of things? You just put that as a circle, I, j. If this product with this one, you get k. This one cross product with this one, you get I. K cross product with I, you get j. That will be way easier for you to memorize everything. Okay? So if your order is opposite, the same law applies, but in opposite direction. When it's in opposite direction, what happens? Negative sign. Okay? So if you use I, j, k, it's positive. If it's j, I, then you get k, but negative. Okay? So if you just want to use this thing and symbolize the calculation procedure, just do it. Because I use this method most of the time. Okay. Questions? Okay? Now, that's introduction and the basic idea of moment. We're going to talk about principles. Okay, this is actually the same as what I just explained to you, but it's a simplified version for two-dimensional calculation. So the idea is, this time I don't have a cantilever. Instead, I have a very weird shape of mechanical components is common, right? When you take your engine apart, no component is actually a regular rectangle or triangle or any kind of those kind of things. It can be very different geometry shape. So if that's going to be the case, what are you going to deal with for the moment when you have a force applied at a specific location? So let's say I have something like this. So we still know the moment, the vector formula over here is still valid. But in this case, I would like to just use the formula which becomes something like this. Okay, so what do I really mean is I have dx over here. For the position over here, I need to locate the coordinate at this point where the force has been applied. So over here, the horizontal distance is dx, the vertical distance is dy. And other than that, you also need to decouple your force into two directions, fx and fy. Now, other than those four things, the other thing you need to know is clockwise is going to be negative, counterclockwise is going to be positive. Assuming all the distance is positive direction, dx is positive, dy is positive because I'm using this one as my reference point or moment center. So f is decoupled into positive and positive direction. So when we are doing that, my moment becomes dx multiplied by fy. So with this force and this moment R, it actually creates a counterclockwise rotation, right? So that is going to give you positive number. If you are using fx, positive fx and positive dy, what happens is this one is going to rotate clockwise. So it's going to give you a negative sign in front of it. So if you don't like to use the vector representation to calculate everything, this is simplified formula you probably want to use. So you might wonder, what if my force is not positive when I decouple them into x direction and y direction? Chances that my F is going to this direction, right? So it's going to be negative force in x direction and still positive force in y direction. How do I modify this formula over here? Right? So the formula itself doesn't really matter because all the numbers we put in this formula, we assume they are positive, right? So if you have a negative force or negative direction in your system, what happens is you're going to carry the negative sign in the individual terms. So the formula still applies, but you need to identify which part or which component here is going to be negative. That's all. When you identify the directions of individual terms, your number will still correct and the formula still applies. Does that make sense to everybody? Okay. I'm going to also prove you can actually use this one, this formula to get the same result. What I mean is, let's say I still want to use this formula. So we know this formula is prepared for 3 dimensions, so we do 3 dimensions. I, J, K. But in this case, we have dx, dy. What am I dk? What am I z direction? 0, right? And over here, what do I have? I have fx, fy. What do I have here? 0. So with the same set up over here, I'm going to get 0 over here. I'm going to get another 0 over here. But I'm going to have a positive number in k direction. So it's going to be dx xy k. And for the other direction, it's going to be negative fx dy k. When I using I direction, I'm going to have a 0 term, so it's going to be 0. When I'm using j term, I encounter another 0, so it's 0. Everybody, so far everybody with me? Knowing what I'm doing using this formula? So, with this set, what do I have? Are they identical? They are, right? So it means that you can, this formula, even though we use our common sense to come up with the answer formula for principal moments, it's actually the same as what we use for three-dimensional calculation with two vectors. They are identical. If they are not identical, then we're in trouble. However, there is one thing you need to be you need to notice. Over here, I'm talking about x direction and y direction. But when I'm talking about the moment, what is its direction? Is that x, y, or z? It's z, right? So what does that mean? It means that you have force, you have moment now. Are you rotating around this thing or rotating around here? No. What is rotated around? Here, right? So, this is x, this is my y. What is this? My z. So that also explains why I have k over here, but when I'm doing calculation, it doesn't really happen. So I have I'm going to apply this formula, okay? I have my x and y over here, and I'm going to apply a force, which is 200 pounds. The angle is 30 degrees. So the problem statement is that a cable attached at B on the L bracket, the tension F in the cable is 200 pounds. Find the moment the cable force creates at the moment center at A. So A is, so what are we given? We are given F equals 200 pounds. And we also give dx equals 2.25 feet, dy equals to 1 feet. What do we need to find? We want to find the moment created at point A. Okay, so this configuration is free body diagram itself, so I'm not going to adjust anything over here. But so far, everybody understand what we're trying to do? So, since we are given these conditions, we can actually use two methods to obtain our result. One is use vector representation, but obviously, most of you guys probably don't prefer to use that method. So we're going to use principle of moments. So when we are using this method, m equals to dx fy minus dy fx. Keep in mind, when you are using this formula, all the individual terms over here needs to be positive direction. Okay, so over here we know that dx and dy are positive numbers. We need to identify whether when we decouple 200 pounds into x direction and y directions, whether they are positive or one of them is going to be negative. But in this case, they are all positive. So if I decouple my f into x direction, y direction, you're going to get it's 173.2 pounds in x direction and 100 pounds in y direction. Both of them are positive. So since we know dx, dy, fx, and fy, we can just apply this number into this equation, and we're going to get n at a equals to 0.25 multiplied by 100 minus 1 multiplied by 173.2. So if you do that, you're going to find this is actually negative 148.2. What do I miss here? Unit. Why is the unit over here? Is that English or is metric? English. So when it's English, it's going to be output. Or full power, it doesn't really matter. And that is going to be my answer. Now, I got a negative sign in front of it. What does that mean? Clockwise. Very good. So this is going to be clockwise. Sometimes I probably won't do this in the exam, but a lot of times when you are dealing with a problem like this, they will ask you whether the thing is going to rotate it clockwise or counterclockwise. The sign in front of the number is going to tell you whether it's going to be clockwise or counterclockwise. So be sure you know what's going on. Okay? So this is another example in your note. Consider the apparatus for exercising the arm in the figure. When the user's elbow is in a fixed position over here, this is fixed, and the cord pulls with a force F that has a magnitude 400 Newton. Find the moment at E created by the cord force. Okay, so still, this is nothing fancy. You just need to know the distance of the moment arm and the force in this configuration. But the problem over here is that everything is indirect. You need to find out the geometry relationship among all distance and the forces. So before we start, we need to identify what are given and what we need to find. Okay? But way before we define those things, one thing you need to determine is this system an English unit system or is a metric unit system? Okay, so when it's a metric, be sure when you see the force or anything, you don't divide that by 32.2 or whatever, okay, because they are not the same. I'm given F equals to 400 pounds, and the length of arm is 300 millimeters, but I would like to use that at 0.3 meter in this case because that will be easier to understand what's going on, and the number is going to be smaller with meter, the unit of meter. Okay, what do I need to find? I want to find the moment created at a fixed position where it is E. So I need to find M at E. So if I want to use principle of moments, I need to find four numbers: dx, dy, fx, and fy. So f is something given, but we are not given the direction of the force. We only know some geometry relationship. We need to know the dx and dy, but in this case, again, we don't really know what happened over here. We only know partial information of this thing. So we need to find out all those information accordingly. Okay, so this is my fixed point. This is where the force has been applied. I know the angle here is 45 degrees. So dx and dy are the easiest two numbers which we can find, which is dx equals to L arm cosine 45 degrees, right? Because the position is between here and here. We know that the length of arm is 300 millimeters. So dx and dy can be found using this setup. So if we do that, it's going to be are they both positive or one of them is negative? In this case, I'm using this one as my moment center. Both of them are positive, right? Okay. Now, we need to find the force, but we know it's 100 Newton. We don't really know where it points to, only with those information over here. So we will need to know the angle. Alpha here first, so we know what's going on. So okay, I know that information, which means I know here is 212 millimeters, right? What do we also know? What is the distance over here? Still the same, right? So far, everybody with me? So with that information, those two pieces of information, this is my alpha, over here. This is a big triangle over here. The height over here becomes what? 212 plus 250. Right. So over here, this is 212 plus 250. How about here? 212 minus 127. Okay, and I'm looking for alpha over here. So we know that tangent alpha equals to 462 over 5. Does it make sense to everybody? Which means alpha equals to arctangent in this case. No. I'm sorry. It's opposite. This should be x, this should be 1. Okay, so when we are doing that, you're going to find this number is actually equals to 10.43 degree. So far, does that make sense to everybody? Is that clear what I'm doing here? Any questions so far? I'm not doing anything special. I'm just trying to identify the direction of this force. So in order to find the direction of this force, the first thing I do is I know the direction of force 400 Newton is over here. So I need to know the triangular relationship on height on the y-axis. So by doing that, I know the relationship is going to be 212 over here plus 250 over here. That is the height of my triangle. And I know distance, this force is going to be pointed to this position based on the problem statement. And this part is 127. And the total width of the bottom over here is 212. So with 212 minus 127, I know the bottom over here is 85 millimeter. So if I know the height is 462 millimeter and the bottom is 85 millimeter, then I should be able to find out the angle alpha over here. So when I know the angle alpha over here, what do I actually talking about? Right? So, can you find the force in x direction and y direction with the angle and the magnitude? It should be straightforward, right? Question: are they positive or negative? Both of them or one of them? Okay, so if we know this information, we're going to get this one is going to be negative 72.41 Newton. This one is going to be negative 393.4 Newton. Okay, now we know our dx, dy, fx, and fy. Principle of moments tells us right? So dx is what is my F1? My dy is what is my dx? What is my fx? Okay, keep in mind this formula over here, or assuming everything is positive. Since we have negative forces over here, you need to put negative sign in front of the forces. Okay, so if when we have this formula and plug in all the numbers, we're going to get our answer becomes, in this case, what is a unit? Metric. Unit meter. Okay. Now we have our answer. Okay. Since we know it's negative, we know it's going to be clockwise. But sometimes you're going to be asked the magnitude and the direction. In this case, the magnitude is going to be what? 68.05 Newton meter. The direction is going to be clockwise. Does that make sense to everybody? Is that straightforward? Everybody understand what I'm talking about? If I give you something like this as a quiz, you guys know how to do it? If this problem in the exam and you have enough time to study, do you know how to solve this? How many of you say I have a problem with this? How many of you say, okay, it looks a little bit weird, but I think I can still do it. Okay. Okay. Okay, so if you guys don't have any questions about this thing, then we're going to move on to the another topic, which is couple. Okay, a couple. Oh, not yet. So fast. Moment. 4. Okay, this is one of the most confusing part in this class. One of them. Okay, so we know three dimensions. So you might have some kind of weird mechanical performance over here, and this is x, y, z, and you apply a force over here. So a lot of time I'm going to ask you, what is the moment created at the moment segment? Oh, let's say O is my reference point. Okay, so what are you going to give me the answer of the moment? Just like what we talked in the beginning of this class, what do we have? We have two things. Position of the vector of the position and what? The vector of the force. So the moment is going to give you with this and with the calculation of this one, right? Nothing fancy. But when you get the answer, you got three numbers in I direction, J direction, and K direction. What does these three numbers actually tell you? I mean, physical meanings. What are the physical meanings of those three numbers? Can anybody tell me? When you say it's going to be MXI, what does this actually tell you? The moment around X direction, the moment around J direction, the moment around K direction, which means when I apply a force to this specific component has a tendency to rotate around this axis, and this axis simultaneously. I know it's somewhat difficult to visualize or imagine how it actually rotates. But if you stop the other two, or you just projected that into X direction, Y direction, or Z direction, you're going to see this one spinning over here, spinning over here, spinning over here. That is how this thing goes. Does it make sense? Okay. Yesterday, we also talked about dot product. You guys remember that? So if I have two vectors, A dot B, what I'm going to have is AX BX plus AY BY. Remember the formula we talked about yesterday? X component multiply component, X component multiply with each other, plus the Y component multiply to each other, and Z component multiply to each other. That is how we define dot product. But physical-wise, what does this actually tell you? What is the physical meaning about the formula I'm writing down? Mathematical-wise, it's really not so difficult to do the calculation. You just take X component out, Y components out, and Z components out, and then multiply them together, add them together, you get your dot product. But when we are talking about mechanics, it has a specific physical meaning. It means that you project your A onto B, which means you would need to know the angle between A and B. So this is the length of A, vector A, this is the length of vector B. The cross product is the lengths multiplied together, then multiply the cosine value of those two things, between those two vectors. Okay? So, what is that important? Now, I'm telling you, I know the moment over here. And I do know the cross product is project one vector onto the other vector. Everybody agree with me for the for the definition over here? What is this? Okay, so the physical meaning of this is that. The physical meaning of this is that. Everybody with me what I'm talking about? Two separate things. Now I'm going to combine those two things together. So, now, I have a mechanical component. I know for instance, your car, your vehicle. So when you put your vehicle into the mechanics, and the technician take everything apart, in their system they use some kind of tools or some kind of hydraulic lifting system to lift up your car, and the coordinate in the garage is a fixed position, which is x and y, x, y, and z. However, there is a component in your car, in your vehicle. It's rotated around some specific angle, and this angle is maybe a wall over here. Okay. Now you will need to know the moment created around this thing. Everybody know what I'm talking about? The scenario I'm talking about. So the moment rotated around the fixed coordinate doesn't really make any sense, because you change your garage, the coordinate is going to be changed, but the relative position may be fixed in your car. So when we are doing that, what am I going to do? What do I need to do? I need to find a way that project this force, this moment, along a specific direction or specific component in your car. Then you really know how much force or moment is actually created along that direction. Does that make sense to everybody? So what are we going to do? We need to know, okay, now I know that the distance related to a specific location, I know the force. So I get the moment with this system. Now, I do know the direction of the specific component I'm interested in. So I need to project this one out to this component. Then we use dot product. Is that clear? Everybody know what I'm trying to do? So if you do know what I'm doing, let's say this specific direction is A. It becomes what? The vector of this specific axis, let's say we should say. Since I say it's a dot product of, I'm actually talking about the dot product of those two things. But this one is something given in your problem statement. You only know the direction and the force, which means it becomes something like this. Okay? So you probably need to calculate this first, then do this. It's more, I wouldn't say it's straightforward, but it's a procedure that I'm talking about so far. We talk about the three-dimensional cross product of the same thing I said, and we talk about that product, two separate things. So you just combine them together, you get the moment projected onto the specific axis that you are interested in. Okay? So can we simplify this a little bit? Yes, because what we're actually doing is x, y, and z. Some of you might say, "Oh my God, how can I? What happened? I need to deal with this again." That's a nightmare. Yes, it is a nightmare. So, can we simplify that a little bit with just one matrix? Yes. And just put ux, uy, and uz. Then you just use one. I know it's still somewhat tedious to calculate, but it will be easier doing this. Okay. However, there is one thing you need to know, which is not specified over here. I'm saying I need to know the direction, the magnitude along this direction. So in other words, u over here is not a random position vector. This one must be unit vector. Okay? Question? No? If not, then we're going to take a 5-minute break. Then we'll come back to explain everything over here.